Okay, let's begin. It used to be thought that the Earth was at rest and the stars went around us. And how could you tell whether or not the Earth is at rest and the stars are going around us, or the stars are at maybe rest, we're going around them? In fact, what's the nearest star? Begins with a S. You might not be knowing this, let me tell you. Begins with a S, ends with an N, got a U in the middle. Try it. Okay? Sun, very good. Okay, that's the sun. Okay, the sun's the nearest star. Okay, and we go around, around the sun. Isn't that true? But it was one time thought that's not the case. And one of the arguments that was advanced to show that the Earth really is at rest and not the other way around is the following. Consider a bird at the top of a tree. And down below, there's a juicy worm just coming up through the ground. And the bird's up at the top and looks down and sees the worm. Now we know from experience that it's possible for that bird to drop from the tree, come down, catch the bird, catch the worm, and fly back up. True? And it was stated as such. It was calculated how fast the world would have to be moving, even turning around like day, night, day, night, day, night. It's about at this latitude something like 800 miles an hour, 800 or 900 miles an hour. Okay? Now, during the time that the bird would let go of the tree and come down, the Earth would race way ahead, and the bird would hit somewhere else. So the fact that that's not the case, in fact, when you drop an object, it will fall at your feet. That is evidence that the Earth must be at rest. Give you an example. If the world is turning this way right now, about 800 miles an hour, watch this. I'm going to stand against the wall. Now, I'm standing on the ground, yeah? I'm moving. The wall's moving. Everything's okay. Well, that's because it was said. That's because I'm anchored to the ground. But what happens when I jump up? Boom! When did that wall boom, hit me? How come? Check your neighbor. Any little rule that we have learned that kind of gets into that and underlies that? A body in motion tends to stay in motion, right? Okay. And so what happens? The bird is moving along 800 miles an hour. The ground's moving along 800 miles an hour. What happens? The bird lets go of the branch. Does it need to hold onto the branch to keep going? Huh? What happens? You get an object in motion, and you don't mess with it. No forces act. What's the object do? Come to a screeching halt? Okay. What's the object do, gang? The object keeps right on going. It used to be said, like, for example, if you want to fly from San Francisco to New York City, all you do is take a helicopter, just go up and wait 3 hours, and the Earth will turn underneath and come back down again. Okay. What's wrong with that? That helicopter doesn't go up and just stay there. That helicopter is moving just as fast as the Earth. And so it just keeps moving around like that, you see? So objects, you're riding an airplane. You've been in an airplane, you flip a coin. When you flip a coin, do you have to adjust for the motion of the plane? Let's suppose you're going this way 600 miles an hour. You may think, man, if I flip that coin, boom, that coin goes bam, 600 miles an hour against the passenger in the back seat. Does that happen? Why doesn't it happen? And what if you were on a plane and someone says, hey, how come, man? I flipped a coin, come right back down. It's not that. I know I'm going 600 miles an hour. When I flipped it, in fact, you ever be on an airplane, you see a fly come by? Man, a fly going 600 miles an hour. With respect to the ground down below. Isn't that true? But how about the coin flip? How come when you flip the coin, it doesn't go in the back seat? What's the coin do? Check your neighbor. The coin keep going along with you, yeah? If you're moving 600 miles an hour, you're holding the coin in your hand, how fast is the coin going? 600. When you flip it, how fast is it going? It's still going 600, 600, 600, because a body in motion tends to stay in motion. Now try this the next time you're at the airport. When you take off and you accelerate, flip the coin. Is it going to land right back in your hand? Check your neighbor. See what your neighbor estimate about that. Now the plane is it's accelerating down the runway. And you flip the coin. Where's the coin end up?
The plane's slowing down. You said when it's landing.
No, not landing. When it's accelerating, going to take off, gang. The plane taking off. You've all felt it. You're sitting there and the plane takes off and you feel it in the back. You feel the seat pushing against your back. You're accelerating. You're accelerating down the runway. Now you flip the coin. Where's the coin end up? Back here or out there? Or back in your hand? How many say right back in your hand? Make no difference, you're accelerating. How many say no, the acceleration makes a difference? I don't know how, but it does. How many say it makes it makes a difference, and I think I be knowing how? Not so many. Now look at this gang. Let's suppose you're coming down the runway. Okay, you're going 50 miles an hour. And just when you flip, you're going 50. This way, huh? Now how fast the coin going as soon as it leaves your hand? 50. But everything's accelerating except the coin, because you let go of it. Now the coin goes up, continues 50, 50, 50. But what do? Now you go from 50 to 60. Hey, sweep the coin back there. See, because the coin's up in the air. Now you've picked up speed. It doesn't. The coins in your pocket do. The coins in your pocket do, because they're forced right along with you. But once you let go of it, it's going to end up in the back seat. If you understand that, if you do, then you can answer this question. Plane's coming in for a landing. It hits the runway. Did you ever see it happen? The exhaust comes out, they got little cups there and turn the exhaust around like a retro rocket. And all of a sudden the plane slows down and you kind of pitch forward. Now you flipped a coin. Front seat, back seat, or right back in your hand while you are slowing down, decelerating. Check the neighbor and discuss what you think it be doing. Okay, gang. How many say this? You know, I think that if that plane's decelerating, it's slowing down. I think if you flip the coin, I think it's going to land up in front of you. Show of hands. Most of the class, yum, 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 yum. Great, that's right, that's right. Because now you're going maybe 50 miles an hour. You flip the coin, it's going 50, but you slow down. Now you're going 40. See, so the coin goes further than you. Can you conceptualize that? The coin's going to go further than you do because you're slowing down. Because nothing's slowing. There's no force acting on the coin now. See, there's a force on you, the seatbelt. That's slowing you down. See, when you accelerate, very, very different than when you're not accelerating. But when you're accelerating, there's got to be some force acting. And when you're not accelerating, all the forces balance out. We can kind of say like that like this. If the acceleration equals 0, if it does, then the net force equals 0. So whenever you're in some object that's not accelerating, all the forces balance out. So when you flip the coin, it's going up. There's no force backwards or forwards. It's going to change the motion of the coin. But if you accelerate and the coin doesn't, then there's going to be a difference in where these two things are going to land. You can kind of see that. We talk about forces. We're going to talk about forces not in terms of pounds, gang, but in terms of newtons. Here's a Newton scale. Here's a kilogram. I'm going to weigh the kilogram. And the kilogram has a weight, gravitational pull, of almost 10 newtons. Want to get strict? 9.8. But we can say 10 newtons. So 1 kilogram weighs 10 newtons. 10 newtons of gravity force. Okay? Like a pound. If I had a pound of butter on here, it would weigh about 4.5 newtons. Or 1 newton's about the weight of a quarter pound of hamburger. What I'm going to do is this, gang. I'm going to pull this block along the table. And I'm going to pull it so it has no acceleration. Let's see if I can do that. Steady, steady, steady. What was the scale reading when I pulled it?
4.
Let me try it again. I'm pulling against friction, isn't that true? There's friction here. It takes a lot to get it started, but once I get it going, steady, steady. What was the force when it was going?
3 newtons.
About 3? 3 newtons is registered, right? Do you know there are people who could watch that and see that it's moving with no acceleration? And they know enough physics, they can say, hey, you know what? I can calculate in my head what the friction force must have been that you were pulling against. And there are people that can't make those calculations. But there are people who can. And all they say is, honey, when you were pulling it, it took 3 newtons to keep it going. I can tell you how much the friction was, so long as it didn't accelerate. See if you're sitting next to someone who can do such a thing in their head. Go. Ooh, heavy, heavy, heavy. When I pull that, I get 3 newtons. There's 3 newtons pulling it this way. Do you guys know anyone who can calculate what the friction must be? Aren't you sitting next to someone? What's the person next to you say? How many newtons of friction?
3 newtons.
How many say 3? Yay, most everybody. That's right. Because if I pulled that and it didn't accelerate, and I know I pulled with 3, wait a minute. If it doesn't accelerate, what's the net force? Is that always true? Yes, it's always true. It's a law of nature. Honey, you show me anything that's not accelerating, and I'll show you something where all the forces balance out to 0. You got it? Something not accelerating, net force is 0. Let's suppose I take this again. And this time I pull it. Watch this. I got more than 3. That time more than 3. See it go up to about 4? If it went up to 4 and the friction was 3, what would the net force be? 1. And a net force of 1, in which direction? That way, and guess which way it accelerated? Do you guys already see that all this stuff we're talking about is common sense? You know what I mean? If you got an extra force that way, guess which way it accelerates? That way, right? And if you got extra force, it's going to accelerate. What if you got just enough force, just to counteract the friction, so the net force is 0? Then how does it move? With no net force, how does it move? Steady, 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 steady. See? But if you get a little bit extra force, and you got a net force that's more than 0, that thing's going to pick up speed. This course can make you popular with people. You're in an airplane someday. You're in an airplane. Someone sitting next to you, very, very delightful. You want to say something maybe that's kind of got some substance, but you're kind of nervous. You know what I'm talking about? You don't say anything. Airplane pilot type over the intercom says, "Okay, gang, we're all flying up here 30,000 feet high. We got a constant velocity of 1,000 kilometers per hour. We got a thrust of the jet engines 18 tons. I'll call you when something else interesting happens." The person next to you says, 1,000 kilometers per hour. Boom, we're pushing 1,000 kilometers per hour through the air. 18 tons of thrust to do that. Whew. We must be really splattering into all these air molecules up here. Must be a horrendous air drag. Then the person says, "I wonder how much the combined force would be of all the molecules splattering against the wings and the fuselage and the tail. I wonder what the combined force of impact would be of all those molecules. I sure be liking to meet someone who could know such things." And you're sitting there and you say, "Santa Claus has come to town. Honey, I can be telling you how much air impact must be." And this person says, "Hey, I'd like having you for a neighbor. You can calculate that, and you can say, in my head." That's the kind of neighbor you want to sit next to, huh? Especially if it's a long flight. Got something between the ears, honey. Can reason things out. By the way, see if you're sitting next to such a person right now. 18 tons of thrust, huh? Constant velocity. Hey, when the dude said constant velocity, that's a little tip-off to a physics type. Because what does constant velocity say about the acceleration? Hey, check that neighbor now, come on. The question, what is the air drag against the airplane? What's the combined force of air resistance? All those molecules splatting against that darn thing, huh? 1,000 kilometers per hour, man, they're hitting. Must be a big friction to go through, huh? How much would it be? Okay, can I have a show of hands of how many people think they might know what the answer is in terms of the tons of friction? Show of hands. Hey, looking pretty good, pretty good, pretty good. And what is that estimate that you have? Someone yell it out. 18 tons. And how do you guys know that the combined splattering of all those molecules add up to 18 tons? How do you know such a thing?
The constant velocity.
Because it's going at constant velocity. And to say it's going at constant velocity, say the acceleration is 0, right? I mean, that's evidence of that, right? And so that means the net force must be what?
0.
But you know there's 18 tons pushing the plane. And then you say there must be an unseen 18 tons pushing back, honey, okay? And so the net force is 0, and the plane continues at constant velocity. It takes 18 tons of thrust to push that plane against 18 tons of air resistance. That makes sense? Now, if you understand that, you can answer this question. What happens if the pilot increases the thrust? More thrust. What happens to the speed of the airplane? Come on, common sense. It accelerates, doesn't it? It accelerates to a higher speed, yeah? Because now you got a net force, right? And as you go faster and faster, what happens to the air resistance? That gets more and more too. So more and more thrust will finally bring you to a higher constant velocity, yeah? Let me ask you a question now. What happens? He cuts down the engines. Boom, cuts them down, cuts them off. Now there's no thrust. What's the airplane do? Decelerate. Why does it decelerate? Why does it slow down? Because now the air resistance is bigger than the thrust. So if there's a net force, there's an acceleration. And we can say that like this. We can say, it turns out that acceleration is directly proportional to the net force. You show me a system that's accelerating. And by that, I mean a system that's changing its speed, okay? Some system that's doing this. It's got a change in velocity over some particular time t. Anything that's changing. You show me a system that's changing how it's moving, and I'll show you a system that must have an unbalanced net force. Makes sense, common sense. If you understand that so far, if you do, if you can understand what this relationship means, it says acceleration is directly proportional to the net force impressed, then you can answer this question. Me and my friends, we're pushing a car. We're trying to get the car started. And we're pushing it, it's gaining speed a little bit. It's gaining speed a little bit. It's not gaining speed enough. We want it to gain more speed. If someone else comes out and pushes also, will it gain more speed?
Yeah.
Why?
More power.
Because there'll be more force. More force, more acceleration. Now I got a question for you. Let's suppose I'm making it accelerate so it picks up like 1 kilometer per hour per second. Let's suppose I want the acceleration to be twice as much. What should the net force be? Begin with a twi. Twice as much. All right, can you do big numbers? Let's suppose I wanted the acceleration to be 7 times as much. How much would the net force have to be? 7 times as much, all right? Can you do fractions? Let's suppose I want the net force to be 9.6 times as much. That's what I want the acceleration to be. What's the net force got to be? 9. You can do decimal. 9.6 times as much. So you see the relationship? So far, easy or hard? E and L? Okay, right on. Okay. Does this hold together so far, gang? All right? All right, now I'm going to take it a further step. I'm going to take a step that maybe, well, let's see what happens. It turns out how much acceleration you get depends something more on how much net force you apply. Because if I push with a net force of so much on a roller skate, I get an entirely different acceleration than if I push like on a Mack truck with the same force. So how much acceleration depends not only on the net force, but something else, gang. What be it? Mass. The mass, the amount of matter, the amount of inertia, you're pushing against, huh? So it turns out the relationship is that. Let me write it down here because I got my chalkboard screwed up a little bit. In chapter 2, we said this is what acceleration is. Acceleration is a change in velocity with respect to time. That's what it is. Acceleration is change. It's change how you move. Now we're saying how you get it, how you produce it. And we're saying now you produce an acceleration by pushing on something, by applying some net force. But how much acceleration depends upon the amount of matter. This idea is Newton's second law of motion. It's powerful. It's probably certainly one of the most important equations in physics. Powerful. It took a powerful mind to figure that out. Let me give you an example. It was Galileo who dropped objects and showed that when you drop them, they will fall together. You do that right here. I've seen this before. I drop them, they fall together. Galileo discovered that. And he found out they had the same acceleration at almost 10 meters per second if air resistance doesn't count. And the thing he found out was that a great big heavy thing doesn't have any more acceleration than a little light thing. And you know what? Galileo was a smart dude, but Galileo could never answer the question HC. He couldn't do it. He couldn't handle it. And the fellow that came along and handled it was after Galileo died. And that's Isaac Newton. Isaac Newton pulled it all together. Interesting. Galileo defined acceleration. He gave to the world this whole idea. And Galileo also talked about inertia before Newton did. And Galileo talked about forces on things. But you know what Galileo never did? He never took all three ideas and pulled them together. Some people are just simple, like, come on, that's heavy. That explains, for example, why these things fall together. Let's suppose you asked a little kid, hey kid, I'm going to drop these two objects. Which one hits the ground first? Now, most kids today, or we all know what the answer is, don't we, gang? What do we say? Same, right? They fall same, right? How come same? Oh, because the acceleration's the same. Well, what's that say? Kind of begs the question, doesn't it? But let's suppose you asked a little kid who was very, very bright, but ignorant. Never seen it before. And you say, kid, I'm going to drop these two objects. You tell me which one hits the ground first. I'll give you a Hershey bar. Kid says, with almonds? Yeah, with almonds too, all right? You tell me which one hit the ground first. And the kid says, well, can I feel those things first? You say, yeah. The kid take this. He says, that's a pretty heavy piece of metal there. It's aluminum, but there's enough of it, so it's kind of heavy. Big gravity force acting on that. Kid take this. Oh, this little tinky ball. See, it's not very heavy at all. That's very, very light. God, doesn't weigh anything. Come on, kid, which one hits the ground first? He says, well, obviously, the heavy metal going to hit the ground before this little red ball. You say, how come? God, what is more force acting on it? I know when I'm pulling my toys, if I pull with a big force, it got a big change in motion. If I pull with a little force, it only change a little bit. There's more force, more gravity force acting on this. Whip, boom, gonna hit the ground. Give me my Hershey bar. Then you take it and you drop these things. And the kid's like, they fell together. Kid doesn't get the Hershey bar. You know what that kid is saying? That kid is saying this, that the acceleration, change in motion, is directly proportional to the force. I got a question for you. Is that kid correct or incorrect? Incorrect. Begin with a C. He's correct. His thinking is fine. But you know what? The experiment doesn't line up with his thinking. One of the beauties of science, we can experiment to see if our thinking is complete. Let's suppose you ask some other kid. He lives in a different part of the island. And you ask the kid the same question. Hey kid, which one going to hit the ground first? The little dinky ball or the heavy weight, huh? And the kid say, can I feel him? And this kid thinks differently somehow. Instead of judging how heavy, what the kid does, he goes like this. Wow, it's pretty hard to change the state of motion of that. Got a lot of resistance to change. Kid takes this. Oh, this little thing here. My gosh, easy to change the state of motion of that. This doesn't have as very much mass. This has a lot more mass. Yeah. This has a lot more inertia. Yeah, come on, kid. Which one hit the ground first? He says, well, this thing here got so much inertia that, of course, the little red ball gonna hit first. He said, the red ball hit first? Yeah. By the time this thing gets around to responding to gravity, whoop, this thing will be already down there. Because I know when I'm pulling things, I'll pull something very light, it, boom, pull something heavy, it lags behind. This thing is gonna lag behind. So the kid says the little ball wins. So you drop the two things, the beauty of the experiment, whoop, the kid. What's wrong? You know what that kid's saying? Is that kid saying something like this? On your toes. Is that kid saying the acceleration is proportional to the amount of mass? Check your neighbor. How many say, no, he ain't saying that? Show of hands. Good. He ain't saying that. He's saying this. First of all, I got to ask you guys all a question. Which number is bigger? How many say, oh, obviously this number is bigger? Show of hands. Get out of here. Get out. Out. No, this is the bigger number, right? Okay? So it turns out that, hey, as the mass gets bigger and bigger, what's the acceleration get? Less and less. So it's this way. This is called an inverse relationship. Make something big, this gets small. Make this small, this gets big. It's upside down. It's inverse. So what the kid is saying is, the more massive, the less the acceleration. See, if I wrote it like this, now the kid is saying, the more massive, the more it will accelerate. No, 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 no. He's not saying that. He's saying the opposite. He's saying the inverse. He's saying this. But you know what? He's incomplete. And this kid, incomplete. Now get these kids together. Get them together, and you talk about some nice physics. Because when you get them together, what do you got? You got what Newton got. You got this right here. Yes, the force. Yes, the inverse mass. Here's the whole thing right there. Yay. Let me show you what I mean. Here's the force acting on this. Here's the force acting on this. Looks like this one gonna be winning, huh, gang? Let me caution you on something. Whenever I ask you to compare the accelerations of different things, acceleration, don't shoot from the hip. Use a crutch. And that crutch is Newton's second law. When I say which of these accelerates more, it's another way of saying which goes faster, which gets down to the ground first, huh? Which accelerates more, use the equation to guide your thinking. Because the acceleration depends not only on the force, but on the what? And what's the mass of this thing, gang? The mass of this thing here is like this. What's the mass of this little dinky thing here? Almost nothing. It's got a mass like this. So are the masses the same? Are the forces the same? Are the ratios of force to mass the same? Do you see that's different? The ratio of both are the same. And that ratio is the acceleration. And they'll have the same ratio, they'll have the same acceleration. If Galileo had known about that, pooh, would have blown his mind. He never got that far. Isaac Newton did. So Isaac Newton was a genius. He pulled it together. And guess what I'm expecting of you folks? To understand what Newton left. It's a legacy. So you're just born at this time and someone tells you, boom, you got it. See that? Works out. I'll tell you when I didn't understand that. When I grew up in Massachusetts, Massachusetts has its own Coney Island, Revere Beach. And I grew up near Revere Beach. And Revere Beach had the roller coaster. You guys be knowing what a roller coaster is? Roller coaster drags you up with a chain up the top of this big hill and then lets you go. And the roller coaster set all these cars, and all these cars would come down like this, and the guy would be standing there, he pulled back on a stick like that. That stick he pulls back on. Between the rails is a board that comes up. And those cars come down, and there's friction, huh? And friction will stop the cars. People get out, other people get on. He takes this big lever and he goes, when he goes like that, you know what happens? The board drops. And now it's on a slight incline. The cars start to go down into a tunnel. All dark down there, scary. Get your money's worth. Little thrill, huh? And you're going down to the tunnel. All gravity feed. Gravity feed. You went down a little hill. You're starting to slow down. You think you're going to run out of gas. And boom! You grab onto a chain. Drag you up at constant speed. When you get at the top, see all your friends down there. You get up the top. Down you go. Here's the thing that impressed me. On that roller coaster ride, that guy with the thing there, that's the only control he had. Because once they're gone, he doesn't have a thing to do until they finally come back again. He's got to remember to pull that thing back so they stop so they don't get an extra ride. But I used to wonder, because sometimes, like on 4th of July weekends and on Labor Day weekends, there'd be lots of people at the beach and they have more than one set of cars at a time. Got about like 2 and 3 sets of cars at a time. And that guy, he was loading them up and letting them go down there as fast as he could. And he wasn't looking at any clock or anything. He wasn't waiting. He was just doing it. I said, what is this guy doing? He's going to be a terrible disaster here. And because I worried about this. Let's suppose one set of cars is loaded up with a whole lot of American Legion conventioneers or something, great big, robust, huge dudes from Texas or something, okay? And they take off, right? But let's suppose before they take off, there's a car loaded with a bunch of little Girl Scouts. Not Girl Scouts, like brownies, like 40, 50 pounders, down in the tunnel first. And these big dudes is following those little girls. Little girls squealing in the tunnel, okay? Yeah, thrilled, huh? What's going to happen if, what happened? Here's the little girls coming up. And behind the little girls, all these heavy, heavy dudes, man, okay? And coming down, I'll just draw one set of cars like this. Little girl there, little girl. This little girl here is under the seat, but she's in front, okay? And following right down behind. Actually, there's a bunch of cars, yeah? I'll just draw one. And coming down behind, it's great big. Coming right down behind these little kids. I think it's gonna be terrible. And so this is Scout's Honor. And what I did, I'd go across the street and I'd watch. And I'd watch for something like this to happen. And I stay all afternoon and watch. I'd go back, you know, several afternoons and watch. And you know, I never saw a case of a very, very lightly loaded car followed by a very, very heavily loaded car. And so in my mind, the solution was, oh, I can see. It's so improbable that they just let that guy load him up as fast as they can, and the chances of it happening worth taking, and that's the end of the story. But it bothered me. It bothered me for years. And when I got into learning about physics and Newton's law, one reading, all of a sudden, boom, flash. I solved the problem. You see, the problem was I thought this is being pulled with a huge force. This is being pulled with a little force. These guys here are going to boom, bang into the kids. But I see it's okay. The little girls are all right. Do you see why the little girls are okay? They're not in danger. It's all right. Check your neighbor. See if your neighbor be knowing. There's a huge force pulling on these guys. There's only a little force pulling on the girls. Shouldn't the guys smack into the girls? Why not? What also do the big guys have besides gravity force? Begin with an M. Mass. Look at the mass of these dudes. It's going to take a big force to get them going. I mean, when an elephant falls off a cliff, you might think it'll just hang there. No, it's got a lot of weight, so it goes. Okay? Two ideas going on, gang. How much force? How much resistance to motion by that force? Inertia, huh? And the little girls, not much force, not much mass. Turns out their acceleration down the incline, is less than the acceleration of free fall. This is not free now. It's constrained with an incline. But they're both the same. And if you take away friction effects, they're exactly the same. And so they both go down the same. Everything is okay. Because you got to think about the amount of mass that's resistant the effects of the force. Kind of neato? Sometimes it's nice when you have a question that burns, and later on you get the answer. Then you remember it. So far, gang, we've been talking about the ideal case of like no air drag, no air resistance. Let's talk about Newton's second law when we have air drag, air resistance. And we can do that by considering a parachute. Because a parachute, I mean, air drag is really, really important there, isn't it? And let's consider the parachutes, just as we have in the text, the easiest case. You know why we're going to take the easiest case, gang? Because the easiest case is enough, okay? We're going to learn the easiest cases. Let's take the easiest case. We have a couple of parachutes, Coney Island style, that are both open and start falling together, okay? But let's have unequal weights. Let's have one parachute like that, the other parachute like that. And this parachute over here is on a kind of a heavy dude here. And this parachute over here is on his little kid sister. Okay? And now they're both coming down. Very heavy, very light. I got a question for you. Which one hits the ground first? Check your neighbor. Through the air. Let me make it really easy. Through a vacuum. which one hits the ground first? Vacuum. Same, same. Someone say, yeah, but this guy's a lot of heavy. You say, yeah, but you got a lot of mass. One effect takes care of the other, huh? But now, air resistance acts. Do you guys think the heavy one's going to hit first? Yeah. How many people say, I think with the air drag, the heavy one guy going to barrel through the air a lot better than the little girl? Show of hands. All right, nice, okay. As they fall, the air drag builds up. I'm going to put an arrow for air drag, and I put the arrow acting up. Why I put it up? Why I put this arrow down? Because weight always acts which way? Begin with a D. Down, okay. And the drag, a resistance force, will always be in a direction to oppose motion. Kind of makes sense, doesn't it? So you're coming down through the air, and the air kind of drags behind, and you're pulling. See? So it's a tug of war between this and this. And let's suppose these are both going the same speed. And I have this one about like that, okay? But let's suppose this over here, let's suppose this is like 400, and let's suppose the girl here is like 150, okay? Let's suppose the air drag here is 100. I got a question for you. Are both of these people at this instant undergoing acceleration? Check your neighbor. Do you know enough physics to say yes or no? Check. How many people say, you know what? They're both accelerating. I ain't going to say they're accelerating the same, but they're both accelerating. Show of hands. Most of the class, good. And how do you know? Because there's a net force. And if you got a net, what's the rule? If you got a net force, there's an acceleration. So look at that. They're both accelerating. Now, as they go faster and faster, what happened to the resistance? Bigger or stay the same? The air drag depends on two things, gang. Depends on how big the thing is, how much air is plowing through, and how fast it's going. You're in the car. You're driving the car. Or your friend's driving the car. You're going 20 kilometers per hour. You stick your head out the window. Feel the air drag? Now the friend's going 50 kilometers per hour. You stick your head out the window. More or less. Now your friend's going 100 kilometers per hour. You stick your head out the window. What do you get? Dandruff job, right? I mean, that air resistance really builds up. The faster you go, the more the resistance, yeah? Okay, so these people are both going to go faster? How do you know they're both going to go faster? Because they're both accelerating. Okay? Now they go faster until the air drag builds up to. I'm making these both pick up the speed the same. I'm really oversimplifying, gang, just to give you the idea. Now they're going so fast that the air drag builds up to 150. I got a question for you. Do they both continue to accelerate? And the answer begins with an N. Okay? Now, which one ain't accelerating anymore? Why the little girl? What's the net force on the little girl? Zero. What's the acceleration of the little girl? Zero. That means the little girl goes, hangs at rest, right? Does zero acceleration mean not moving? No. Zero acceleration means not changing how you is moving. Okay? So she continued down, steady. Let's suppose right now she's going maybe 30 kilometers per hour. 30 kilometers per hour at this point. Wait a couple of seconds later. How fast is she going? 30 kilometers per hour. How about the dude? He's going faster. He's going faster. He's picking up. She stopped picking up. What's the 50-cent word for stop? Terminate. Her acceleration has terminated. She says, I have reached my terminal velocity. I'm going so fast that the air drag against me, honey, exactly equal to gravity pulling down, it's a wash. The net force on me is zero, so I go steady, all the way down with no acceleration at all. Ain't that neat? Is that understandable? Yeah, it kind of holds together, doesn't it? You can see that. You go outside with your friends. You see a leaf fall off the tree. The leaf just kind of floats down, no acceleration. You say to your friend, you know what? I know how big the air drag is in that leaf compared to its weight. And your friend say, you know that? And I say, I do. And what is it? Check the neighbor. I say, I don't know what the hell the air drag in the leaf is. How do I be knowing? Come on, what is it? See if you're sitting next to someone don't know. How many say, hey, believe it or not, Hewitt, everything you said, this person here don't know the answer. Put up the hand. Go like this to the person. Really? Really? Okay. Hey, we all get this stuff, huh? All right. Okay, gang, so far we've talked about Newton's first law, yeah? And today we talk about Newton's second law. Guess what we're going to be talking about next Wednesday? Newton's third law, all right? Get this stuff down. I'll see you next Wednesday. Yay.